Welcome to Between Sleep and Science, a quiet space online where deep contemplation and calm coexist. If you're settling down for the night, please make yourself comfortable. Let the urgency of your day gently fall away, allowing your thoughts to drift along the unhurried tempo of science told softly. In the rigid discipline of formal science, it is considered an intellectual transgression to speak of coincidence. Yet this story, the narrative of the greatest mass extinction event in our planet's 4.5 billion year history, is utterly interwoven with an astonishing series of seemingly chance occurrences, years of bureaucratic secrecy, and moments of brilliant serendipitous deduction. We are universally taught the simple, definitive truth. A colossal asteroid ended the magnificent reign of the dinosaurs. But if this single fact is the undisputed answer, then why did it take the finest geologists, cartographers, astronomers, and satellite analysts in the world nearly 3 decades to find the impact site? It was as if an immense, unseen force, whether geological, the slow creep of tectonics, or perhaps even human, the sealing of classified archives, had labored tirelessly to wipe the colossal scar of the 180-kilometer-wide crater from the visual record of the Earth. If these quiet wanderings bring you even a moment of calm, feel free to leave a few warm words, or tell us in the comments which city you're watching from, so we can see how far our explorations travel. You can also simply like and subscribe. Your support helps other weary hearts discover this cozy corner. And now, you don't need to do anything at all. Just settle in comfortably and let the slow, steady rhythm of deep time gently carry you away from your worries. Let the journey begin. Could the accepted asteroid theory be an oversimplification, a mere explanation for the how without touching the why? Is it possible that the impactor was merely a devastating symptom, a visible consequence of forces far grander, more terrifying, and fundamentally cyclical, forces tied directly to the very architecture of our galaxy, the ebb and flow of stars, and the mysterious, invisible substance known as dark matter that binds all structures together? We will delve into the disquieting theory that mass extinction on Earth is not random, unpredictable chaos, but a scheduled clockwork event, synchronized with an ancient cosmic pendulum set by galactic tides. And the final, most infuriating puzzle, a testament to the conflict between commerce and discovery. Why did the crucial data, the definitive proof that confirmed the truth and ended decades of scientific warfare, lie dormant and classified for years in the dusty, locked filing cabinets of a multinational oil corporation? The answer, as we shall see, involves all these threads. Perhaps the rock we dismiss as a stroke of cosmic bad luck is, in reality, a fragment of a giant universal timepiece poised in the cosmic dark, waiting to mark its next destructive hour. To begin our investigation, we must deliberately turn our gaze away from the cold vacuum of space and descend to a location that appears utterly divorced from any celestial catastrophe. A serene, sun-drenched canyon in Italy, tucked away in the picturesque vicinity of the medieval city of Gubbio. This is precisely where the paper trail begins, 66 million years later. To truly appreciate the seismic magnitude of the discovery that began to unfold in Gubbio during the 1970s, one must first immerse oneself in the prevailing, unquestioned orthodoxy of geological thought at that time. The entire discipline was governed almost to the point of religious doctrine, by the doctrine of uniformitarianism. The core tenet was elegantly simple, yet deeply restrictive. The present is the key to the past. This philosophy dictated that the Earth's majestic physical features, its mountains, oceans, and valleys, were shaped exclusively by continuous, gradual forces, operating at the same slow, inexorable pace witnessed today, but stretched across incomprehensibly vast timescales. Mountains grew imperceptibly over millions of years, oceans advanced and receded over countless generations, and life forms, following suit, vanished slowly, unable to keep pace with minute, subtle shifts in global climate or competitive pressures. In this scholarly environment, dominated by the intellectual legacy of James Hutton and Charles Lyell, to utter the word catastrophe was akin to intellectual heresy. To suggest that a global geological layer, a whole page in the Earth's history, could have been formed instantaneously by a cataclysmic event was to risk immediate condescending dismissal as a charlatan, a fantasist, or a naive amateur. The academic world prized stability, demanded predictability, and scorned any hint of sudden planet-altering violence. It was into this atmosphere of tranquil yet rigid academic conservatism that the American field geologist Walter Alvarez arrived. His expertise was niche. He was a specialist in paleomagnetism, the intricate study of how the Earth's magnetic field orientation is recorded like an invisible compass within the chemical structure of rock strata over time. Walter's primary interest lay neither in the vanished life of the ancient world nor in the cold mechanics of outer space. He was concerned with identifying and dating the periodic reversals of the Earth's magnetic poles. The canyon walls near Gubbio provided him with the perfect, unblemished geological ledger. These were layers of compacted marine limestone, known locally as scaglia rossa, meaning pink scale, which had settled gently and continuously onto the floor of a primeval sea for tens of millions of years. Within these dense, fragile strata were embedded billions of microscopic fossils, the tiny, intricate, chambered shells of foraminifera. These minute organisms, the plankton of the ancient oceans, lived, died, and rained down ceaselessly, creating a meticulous, unbroken, page-by-page history of oceanic life. Walter used the magnetic stripes recorded in the rock, the periodic flipping of the north and south magnetic poles, to assign precise dates to each layer of limestone. As Walter began his painstaking work, chipping samples chronologically up the rock face, moving from the deep past toward the future, the record was vibrant. The Cretaceous layers were full of life. The foraminifera fossils were complex, large, and astonishingly diverse, indicating a thriving ecosystem. Then, suddenly, at a precise geological coordinate, the story broke. The record was violently interrupted. Lying directly between the life-rich Cretaceous layer and the subsequent sparse Paleogene layer was a boundary of clay. It was unassuming, dusty, and almost easy to miss. No more than a single centimeter thick. But inside that fragile, razor-thin layer, the entire history of life was silenced. The fossils vanished. The complex marine ecosystem, the foundation of the oceanic food web, had utterly collapsed. Immediately above it, the limestone resumed, but the microscopic shells were now rudimentary, meager, and almost featureless. A desperate, rudimentary reboot of life, dominated by species that were tiny and simple. It was an instant, violent, and undeniable change in the geological script. This thin geological signature marks the KPG boundary, Cretaceous-Paleogene, the dividing line between the Mesozoic and Cenozoic eras, representing the exact moment 66 million years ago when the great terrestrial reptiles vanished. But for Walter, the pressing issue was a technical one, a question of time. He needed an absolute chronological marker. How long did it take for that solitary centimetre of clay to settle? If the clay itself was deposited over thousands of years, the uniformitarian model of slow decline would hold sway, fitting neatly into the established academic comfort zone. But if it formed in months or years, the scientific world would be forced to confront the unimaginable violence of a true global catastrophe. The clay itself provided no means of dating. To unlock this fundamental problem of geological time, Walter turned to the one person he knew possessed the radical genius necessary to think beyond the terrestrial boundary: his father, Luis Alvarez. The resulting partnership between the geologist's son, Walter, and the physics titan, Luis Alvarez, became one of the most consequential scientific collaborations of the 20th century. Luis Alvarez was a man of monumental stature, a Nobel laureate in physics, 1968. He had been instrumental in the secret development of the detonators for the atomic bomb in the Manhattan Project, and had pioneered techniques to probe the internal structure of the Egyptian pyramids using cosmic rays. He possessed an extraordinary, almost Renaissance combination of theoretical brilliance, lateral thinking, and practical engineering savvy, a mind uniquely unconstrained by the dogma of any single field. When Walter presented the dilemma of the centimetre-thick clay layer, the layer of missing time, Luis immediately proposed a solution of breathtaking elegance and extraterrestrial perspective. Use cosmic dust as a measure of geological time. Our planet, Luis reasoned, is constantly receiving a gentle, steady drizzle of micrometeorites, cometary tails, and solar system debris. This microscopic dust is chemically distinct. It is rich in platinum group metals, most notably iridium. On Earth, iridium is exceptionally rare. Being a siderophile, or iron-loving element, virtually all of it sank to the planet's core during its early molten formation. Consequently, in the Earth's crust, iridium is practically non-existent. In the cold vacuum of space, however, it is relatively abundant, a constant, tiny marker of extraterrestrial infall. Luis Alvarez's logic was a stroke of genius, both simple and profound. Cosmic dust rains down at a consistent, measurable rate. Therefore, if the boundary clay layer represented thousands of years of sedimentation, it must have accumulated a significant, measurable amount of cosmic iridium. Conversely, if the layer represented a geological instant, a single decade or less, the iridium levels would be undetectable, barely registering above the trace background levels. The concentration of this rare element would provide the definitive chronometer. They sent samples of the boundary clay to the specialized laboratory of nuclear chemists Frank Asaro and Helen Michael at the Berkeley lab. Their task was technologically daunting: to find a substance present in concentrations as low as a few parts per billion. They employed the most sensitive technique available: neutron activation analysis, NAA. This intricate process involved placing the clay samples inside a nuclear reactor, bombarding them with a dense flux of neutrons to transmute stable iridium atoms into a temporary radioactive isotope, iridium-192. By then, measuring the unique signature of gamma radiation emitted during the decay of this new isotope, they could quantify the presence of iridium with incredible atomic-level precision, revealing even the most minuscule trace amounts. The results, which arrived in the summer of June 1978, were not merely surprising. They were seismically shattering, instantly obliterating the foundations of uniformitarian geology. Walter and Luis had cautiously anticipated, at best, a small, modest accumulation of iridium, suggesting perhaps a few millennia of slow deposition. Instead, the instruments registered an anomaly that was impossible to dismiss. The iridium concentration in the Gubbio clay was an astounding 30 times the normal background value. The initial logical scientific response was disbelief. Contamination had to be the cause. They hypothesized an error. Perhaps a lab worker's platinum wedding ring had accidentally tainted the sample. They meticulously rechecked every possible source of error. The finding held absolutely true. To rule out a local geological anomaly, Walter immediately traveled to Stevens Klint, Denmark, another globally recognized site where the KPG boundary was exposed in towering sea cliffs. The analysis from the Danish site was even more dramatic, showing an iridium concentration 160 times the background level. Quickly, identical non-local anomalies were confirmed by independent researchers in New Zealand, Spain, and from deep-sea cores extracted from the floor of the Pacific Ocean. The conclusion was inescapable. This was not a regional Italian peculiarity. A thin, distinct layer of cosmic material had been deposited synchronously across the entire planet 66 million years ago. The iridium was a universal calling card, marking a planetary event of singular importance. The question of its delivery system narrowed. Luis Alvarez first hypothesized a massive proximal supernova explosion occurring near the solar system. A star detonating could indeed bathe the Earth in heavy elements. This theory was appealing, as the intense blast radiation might also explain the mass extinction. To test this, the chemists searched for plutonium-244, a short-lived isotope characteristic of recent supernova remnants. Since plutonium-244 has a half-life of only 80 million years, it should have been present in the supernova debris, but would have decayed entirely in our 4.5 billion-year-old system. They searched exhaustively. They found none. The absence of the specific isotope conclusively eliminated the supernova hypothesis. The only remaining profoundly disturbing possibility was that the iridium came not from a distant star, but from a collision within our own solar system. It was a massive asteroid or a comet. Luis Alvarez then undertook the terrifying task of calculation. By utilizing the total global concentration of iridium and the average density of iridium known to be present in stony meteorites, specifically unrefined chondrites, he could reverse engineer the required size of the impactor. The numbers that emerged from his equations were staggering. To lay down such an even global layer of cosmic material, the object had to be approximately 10 kilometers in diameter. 10 kilometers of solid rock and metal, arriving at a speed of roughly 20 kilometers per second. The energy released, calculated using the kinetic energy formula E equals 1/2 mv squared, was beyond human comprehension. The calculated impact energy was roughly 100 million megatons of TNT equivalent. To grasp the scale, the Soviet Union's Tsar bomber, the most powerful nuclear weapon ever tested, yielded 50 megatons. The asteroid strike was 2 million times more potent. The mathematics demanded a catastrophic event. In 1980, the Alvarez team published their definitive findings in the journal Science. It was titled Extraterrestrial Cause for the Cretaceous Tertiary Extinction. It was not merely a scientific paper. It was a brazen declaration of war on the established geological order, instantly triggering the greatest scientific controversy of the decade. The invisible scar, the geopolitical cover-up, and the rediscovery. The reaction from the entire geological and paleontological establishment was immediate, intense, and sustained. For decades, these scientists had meticulously constructed intricate, slow-motion narratives of dinosaur decline, gradual falling sea levels, subtle climate shifts, and evolutionary decline. The idea that this grand, complex biological drama could be reduced to a single, random, catastrophic rock falling from the sky was seen as a profound simplification, an insult to the subtlety of evolutionary history. The ensuing scientific conflict raged in academic journals and at fiery conferences for years. Opponents pointed to the powerful volcanic theory. They cited the enormous flood basalt eruptions in the Deccan Traps, India, which occurred around the same time, spewing vast quantities of ash and gas that could have caused climate change and, potentially, even supplied some of the iridium. Geologists argued that the Deccan Traps eruptions lasted for hundreds of thousands of years, a continuous global assault on the environment, perhaps a sufficient trigger for mass extinction without a space rock. However, later isotopic analysis comparing the iridium signatures of the boundary clay and the volcanic basalt would ultimately prove the iridium was definitively extraterrestrial. But the single, most decisive and logical weapon wielded by the critics was the question that hung over the entire debate like a shroud. Where is the crater? Calculations mandated a crater at least 150 to 200 kilometers in diameter. Such a colossal structure, a wound the size of a small country like Belgium, should have been immediately visible from space. Geologists examined every corner of the continents, reviewing all available aerial and satellite imagery. No crater of the required size and, crucially, the right age, 66 million years, could be found. The skeptics held an unassailable logical position. No hole, no hit. The Alvarez theory became an irresistible paradox. Irrefutable chemical fingerprints found globally, yet no physical crime scene. The solution, tragically and ironically, was not hidden in space, but under the Earth's surface, and under thick layers of corporate and geopolitical confidentiality. Our narrative shifts dramatically to the sun-drenched Yucatan Peninsula, Mexico. Today, this area is globally synonymous with idyllic azure waters, pristine white sand beaches, and the ancient ruins of the Maya. Tourists enjoy cocktails, utterly unaware that they are sunbathing directly atop the sealed tomb of the Mesozoic era. To uncover the truth, we must adopt the pragmatic, commercially focused perspective of the oil industry. In the late 1970s, at the very moment Walter Alvarez was analyzing his clay layer, a young American geophysicist named Glenn Penfield was working for the Mexican State Oil Company, PEMEX. His sole mission was pragmatic and commercial, to locate geological traps capable of holding vast oil deposits. To achieve this, geophysicists employ techniques that can see through kilometers of subsurface rock. Penfield was meticulously mapping the area using both magnetometry, measuring subtle shifts in the magnetic field caused by different rock densities, and gravimetry, measuring slight density variations that affect gravity. In 1978, Penfield was reviewing the compiled magnetic maps of the Gulf of Mexico when he noticed an immense, strange, and perfectly regular arc in the northern Yucatan. It was a massive, semicircular magnetic anomaly. When he superimposed his gravity data, the inland portion of the arc was perfectly revealed, forming a colossal, nearly perfect circle of approximately 180 kilometers in diameter. The center lay precisely near the inconspicuous fishing village of Chicxulub, a Maya name that translates, with chilling prophecy, to the demon's tail, or demon of the flea. Penfield instantly recognized the features. The symmetry, the sheer size, and the distinct central peak structure, a classic rebound bulge typical of hypervelocity impact sites, meant this was unequivocally not a volcano. He had found one of the largest impact craters on Earth. But here, the plot thickened into a true scientific tragedy. The maps and all the underlying geological data belonged exclusively to PEMEX. Information on the deep subsurface structure was considered a commercial secret worth billions of dollars. The company management strictly forbade Penfield from publishing the detailed geological maps or precise coordinates. For a critical decade, the irrefutable proof, the smoking gun, lay locked in a corporate safe in Mexico, while the Alvarez team fought for their theory's survival against the entire scientific establishment. In 1981, the year after the Alvarez paper was published, Penfield and his superior, Antonio Camargo, attempted a desperate public break of the silence at a Society of Exploration Geophysicists conference. They presented a poster on the bizarre Yucatan structure, but the audience was composed of hard-headed oil prospectors, not paleontologists or astronomers. The talk was too far outside their commercial scope. Penfield's report was ignored. Critically, he still lacked a precise way to date the structure to 66 million years ago. The world was not ready, and the discovery slipped back into shadow. The deadlock finally broke in the early 1990s. Alan Hildebrand, a fiercely determined graduate student at the University of Arizona, made it his personal mission to find the missing crater. He reasoned that if the crater couldn't be found, its debris must be. He searched not for the crater itself, but for the debris flung from the blast site, tsunami ites, sedimentary evidence of immense megawaves deposited from the impact, and tektites, tiny solidified glass droplets of molten rock ejected into space and rained back down. All the debris layers converged, pointing relentlessly toward one general area, the Gulf of Mexico. Hildebrand was eventually guided by a reporter who remembered Penfield's obscure 1981 presentation. The subsequent phone call between Hildebrand and Penfield became one of the most pivotal moments in geological history. "I think I know where your crater is," Hildebrand said. "I know where it is too. But no one believed me," Penfield confirmed. They now needed the final, undeniable physical evidence. And in a final, staggering twist of fate, it was discovered that Pemex had unknowingly drilled exploratory wells right into the heart of the crater decades earlier, in the 1950s, mistaking the dense, impact-altered core for a potential oil dome. The logs had simply described the findings as volcanic rock. After a relentless, years-long search, a few surviving core samples were located, found literally in a pile on the back lot of one of the company's storage facilities. When these unassuming core samples were placed under the laboratory microscope, the mystery was solved forever. The rock contained unmistakable shocked quartz. The crystal lattice of quartz is extremely robust. To fracture it in the specific microscopic way visible in the cores requires pressures found only in two environments: a nuclear explosion or a hypervelocity asteroid impact. No volcanic or tectonic force on Earth can produce this effect. The simultaneous chemical analysis confirmed the rock was an explosive blend of Earth limestone and the same iridium-rich meteoritic material the Alvarez team had found years earlier. In 1991, Hildebrand, Penfield and their colleagues published their definitive findings. The Chicxulub crater, 180 kilometers wide, was dated with irrefutable precision to 66 million years ago. The invisible scar had finally been found, buried deep beneath kilometers of subsequent sedimentary rock. The calculus of annihilation, shock physics, and the vaporized assassin. The location was verified, but the central, counterintuitive paradox remained the most fascinating piece of the puzzle. Where was the body of the assassin? The hole was 180 kilometers wide, but the impactor was only 10 kilometers in diameter. 10 billion tons of solid matter cannot simply vanish. The answer is found not in geology, but in the realm of extreme hypervelocity physics. We must abandon all our everyday notions of solid objects colliding. The key factor is the sheer velocity. The Chicxulub impactor struck the Earth at speeds around 20 kilometers per second, 72,000 kilometers per hour, more than 20 times the muzzle velocity of a high-powered rifle bullet. At this hypervelocity, the object's kinetic energy is so monumental that it utterly overwhelms the molecular and atomic forces holding the rock together. As the physics formula for kinetic energy E equals 1/2 mv squared dictates, the mass of the projectile is less important than the square of its velocity. Doubling the speed quadruples the energy. At 20 kilometers per second, the energy release transcends normal mechanics. The moment the asteroid tip touched the surface of the ocean, it initiated a phase transition of terrifying instantaneous speed. The solid rock didn't just shatter. The intense pressure and energy instantly forced it to skip the liquid and gas phases, turning it directly into a superheated ionized gas, plasma. The asteroid's tail was still 10 kilometers up in the atmosphere, while its front end had been completely arrested by the planet's crust. The object effectively compressed and annihilated itself under its own colossal momentum. Pressure at the impact point reached millions of atmospheres, pressures only seen inside the Earth's core. Temperatures soared to tens of thousands of degrees Celsius, hotter than the surface of the Sun itself. The asteroid and a massive section of the Earth's crust beneath it were instantly vaporized in a blast that resembled a colossal planetary-scale hydrogen bomb. The resulting vapor plume, an immense column of superheated plasma consisting of both asteroid and vaporized rock, was ejected back into space. This explains the mystery. The asteroid was never found because it didn't settle on the crater floor. It became the explosion itself. The matter of the C-type chondrite mixed with the vaporized Earth rock and was then flung into the stratosphere and beyond. As this plume cooled and condensed, the iridium-rich material clumped into microscopic dust, raining back down over the next few months to cover the entire globe, the same 1-centimeter clay layer Walter Alvarez had found. The assassin was not hiding. It was the very dust coating the world. Computer modeling, particularly the work of Gareth Collins and his team, 2020, revealed another deadly factor: the angle of impact. The asteroid struck at a near-optimal 60-degree angle to the horizon. A direct 90-degree hit would have buried most of the energy deep into the Earth's mantle, containing the worst of the fallout. A shallow, glancing blow would have sent most of the energy ricocheting back into space. The 60-degree angle was the perfect geometric scenario for maximum atmospheric disruption, maximizing the ejection of vast quantities of rock, dust, and critical climate-altering gases into the stratosphere. It was, in effect, a cosmic sniper shot. The physics of the crater formation itself is equally astonishing. The shock wave was so intense that the Earth's crust momentarily behaved like a fluid. A transient cavity formed, miles deep, whose walls immediately collapsed inward and upward. This produced a rebound, a mountain of semi-molten rock that momentarily towered 10 to 15 kilometers high, higher than Mount Everest, before collapsing back down. This collapse created the distinct, concentric ring structure that Glenn Penfield saw in his gravity maps, a frozen ripple on a colossal stone pond. The final confirmation of the killer's identity came in 2024. A team led by Mario Fischer-Gödde used high-precision analysis of ruthenium isotopes in the boundary layer. The isotopic ratios of ruthenium function like a genetic fingerprint, distinct for different regions of the solar system. The ruthenium signature was an unequivocal match for carbonaceous chondrites, C-type asteroids. These are the rarest, darkest, and most primitive bodies, originating from the cold outer solar system beyond Jupiter's snow line. The irony remains profound and chilling. C-type chondrites are rich in organic compounds and water. They are the same class of objects believed to have delivered the fundamental building blocks of life to the early Earth. The object that may have seeded life returned 4.5 billion years later to nearly extinguish it, the perfect storm of death and the mechanism of extinction. The impact was localized to the Yucatan Peninsula, yet the extinction was global. The Triceratops munching on ferns in Mongolia, or the pterosaur soaring over Antarctica, was not crushed by a rock. They perished because the Earth's delicate life support system was systematically and universally broken. The extinction was not a single moment, but a complex, escalating perfect storm, a cascade of physical, chemical, and biological disasters. The first immediate disaster was light and heat. In the fraction of a second the blast energy was released, it created a blinding flash across half the globe, instantly searing everything in view. But the real killing mechanism began minutes later. The trillions of tons of melted rock and crust ejected during the impact, the tektites and spherules, began to re-enter the atmosphere globally. This re-entry phenomenon turned the entire sky into an incandescent, glowing blanket. Every re-entering particle became a miniature shooting star, and the friction heated the entire atmosphere to incredible temperatures. Computer models suggest the global surface temperature may have briefly spiked to 200 to 300 degrees Celsius. This was the terrifying oven effect. Everything that could not burrow deep underground, dive deep under the water, or find solid rock shelter was cooked alive. The great dinosaurs, lacking such refuges and possessing thick hides that couldn't dissipate heat fast enough, perished from hypothermic shock. Global forests were instantly ignited, creating a massive planetary firestorm. The resulting charcoal and soot layer found in the KPG boundary sediments confirms this fiery apocalypse. The terrestrial environment was consumed within days. For the survivors, the small mammals, tortoises, and crocodiles that sheltered underground or in water, the second, slower disaster was cold and darkness. The geography of the impact site sealed the planet's long-term fate. The Yucatan seabed was not just granite. It was rich in sedimentary rocks containing immense deposits of gypsum and anhydrite, which are full of sulfur. The vaporization of these rocks hurled billions of tons of sulfur compounds into the stratosphere. Up there, the sulfur combined with water vapor to form vast reflective clouds of sulfuric acid aerosols. These sulfate particles acted as a powerful mirror, reflecting incoming sunlight directly back into space. The Earth was plunged into a sunless twilight, an asteroid winter. Photosynthesis collapsed. Without sunlight, plants on land and phytoplankton in the ocean, the foundation of the entire food web, died. Herbivores starved, and the mighty carnivores followed. The Tyrannosaurus rex that survived the initial flash and firestorm died slowly of starvation and cold in a world where the sun was eclipsed for years. The subsequent acid rain further devastated marine ecosystems, dissolving the calcium-based shells of any plankton that survived, causing a complete collapse of the food chain from the bottom up. The key to survival lay in size and diet. The mammals of the time were small, rat-like, and masters of burrowing, which saved them from the heat. Crucially, they were omnivorous, able to subsist on roots, seeds, insects, and carrion, anything that could be scavenged in a devastated dead world. The highly specialized, large-bodied dinosaurs required vast quantities of fresh food, a need that became impossible to meet. The catastrophe was a brutal lesson in evolution. Survival favors the flexible, the small, and the non-specialized. This tragic story is amplified by the sheer bad luck of location. Had the asteroid struck just 30 minutes earlier or later, the Earth's rotation would have placed a deep section of the Pacific or Atlantic Ocean at the point of impact. These areas lack the immense sulfur-rich gypsum deposits of the Yucatan. The resulting global winter would have been less severe, and the dinosaurs might have survived the ensuing darkness, leaving a vastly different evolutionary path for the planet, one in which humankind may never have emerged. We are, quite literally, the children of this cosmic accident. The rhythms of extinction and the dark matter conductor. Having unraveled the catastrophic mechanism of death, we are left with a persistent and profound philosophical question. Was the Chicxulub impact merely a random event, a black swan that could never be predicted? Or is mass death on Earth a scheduled, repetitive pattern? The human mind naturally seeks patterns in chaos. In the 1980s, shortly after the Alvarez discovery, two brilliant paleontologists at the University of Chicago, David Raup and Jack Sepkoski, performed a monumental historical audit. They analyzed every known mass extinction event over the last 250 million years, using the fossil records of marine life as their metric. Their finding was both scientifically brilliant and psychologically chilling. Extinctions were not scattered randomly across the timescale. They occurred in a terrifying rhythmic beat, repeating approximately every 26 million years. 26 million years of life, followed by a global catastrophe, followed by another 26 million years of calm. This discovery immediately fueled the controversial Nemesis hypothesis. Scientists posited that the Sun had an unseen companion, a dim red or brown dwarf star they dubbed Nemesis, orbiting our star in a highly elliptical, distant orbit. Every 26 million years, this Death Star would swing close to the Oort cloud, the vast spherical reservoir of 1 trillion icy bodies surrounding the solar system. And its massive gravitational pull would destabilize the comets, sending a lethal, concentrated shower toward the inner planets, including Earth. Despite decades of exhaustive searching, using powerful infrared telescopes like WISE, no such companion star has ever been definitively found. The Nemesis star hypothesis, for lack of a body, died. But if a killer star is not the conductor, what is setting this immutable cosmic rhythm? This question brings us to modern theoretical physics, and to the groundbreaking work of Lisa Randall, a theoretical physicist from Harvard. In her hypothesis, she makes a profound connection, linking the fate of biological species on Earth to the most enigmatic substance in the cosmos, dark matter. We know dark matter exists because we observe its immense gravitational effect. It provides the glue that prevents galaxies from flying apart. Randall proposed a specific nuance, that a small fraction of dark matter might interact weakly with itself and cool, causing it to collapse into a dense, thin disk embedded directly within the visible plane of the Milky Way. Imagine our galaxy, the Milky Way, as a giant, warped vinyl record. Our solar system is part of that disk, but it is not static. It oscillates, moving up and down in a wave-like motion like a horse on a galactic carousel. The Sun passes through the densest part of the galactic plane, and through this hypothesized dark matter disk, roughly every 30 to 35 million years, a period strikingly similar to the observed extinction cycle. Randall's hypothesis suggests that when the solar system plunges through this hypothetical dense dark matter disk, the localized gravitational force sharply increases. While dark matter particles cannot physically hit us, their collective gravitational tide is enough to violently perturb the Oort cloud. The Oort cloud, a trillion-strong swarm of icy bodies, is held in a fragile, distant equilibrium by the Sun's gravity. The gravitational shock from the dark matter disk is enough to knock millions of these comets from their stable orbits, sending a devastating barrage toward the inner planets. The implication is profound and terrifying. The dinosaurs may have died not because of a single random rock, but because the solar system, in its ancient gravitational dance around the galactic center, dipped into an invisible dark river. Earth's biology is, therefore, intrinsically linked to the astrophysics of the Milky Way. We are not an isolated system. We are a vital part of a vast, breathing, and dangerous galactic organism. The calculus of chaos and the unseen forces of prediction. While the dark matter hypothesis addresses the long-term, deep time cycle, chaos reigns supreme in the shorter term. We face two immense challenges in predicting the next impact event: the instability of the n-body problem and the insidious, non-gravitational Yarkovsky effect. Celestial mechanics is not a perfect, stable clock. The moment a third gravitational body is added to a simple two-body system, like the Earth and Sun, the equations spiral immediately into a chaotic, generally unsolvable nightmare. This is the famous three-body problem, a concept formalized by the great French mathematician Henri Poincaré in the late 19th century. Minor shifts in initial conditions, moving an asteroid a single meter or changing its velocity by a millimeter per second, result in wildly divergent and unpredictable orbits a century later. This is the butterfly effect applied to space. The main culprit and gravitational architect of this chaos in our solar system is the gas giant Jupiter. Its colossal mass, 318 times that of Earth, constantly tugs and perturbs the orbits of passing asteroids, effectively turning the inner solar system into a massive, unpredictable gravitational pinball machine. But the most insidious threat to precise long-term prediction is a force so small it seems utterly irrelevant: the Yarkovsky effect. Discovered by the Russian engineer Ivan Yarkovsky in the late 19th century, this effect is subtle yet constant and cumulative. An asteroid absorbs sunlight, heating up one side. As the asteroid rotates, the heated surface faces away from the sun and begins to cool, emitting thermal radiation, infrared photons, into space. Because photons carry momentum, this constant emission of heat acts like a tiny microscopic rocket thruster, constantly nudging the asteroid in the opposite direction. This physical force is often compared to the weight of a paperclip. But because it acts continuously, year after year, century after century, the cumulative effect over deep time is monumental. Over decades, this thermal engine can shift an asteroid's position by hundreds of kilometers from its purely gravitational orbit. For the purposes of precise trajectory prediction, a 100-kilometer shift is the crucial difference between a harmless miss and a direct impact. The Yarkovsky effect is why long-term orbital predictions are so difficult. To calculate an asteroid's position 100 years out, we need to know not only its mass and velocity, but also its spin rate, its precise color, darker absorbs more heat, and its thermal conductivity. We need the thermal map of a rock millions of kilometers away. This complexity led directly to NASA's OSIRIS-REx mission to Bennu, which confirmed that this asteroid is drifting off its predicted orbit by 280 meters per year due to solar heating. The difficulty of this predictive calculus was brutally underscored by the Chelyabinsk meteor incident on February 15, 2013. On a routine winter morning in Chelyabinsk, Russia, the sky was momentarily brighter than the sun. A 20-meter rock, weighing over 10,000 tons, exploded high in the atmosphere with the energy of 500 kilotons of TNT, 30 times the destructive power of the Hiroshima bomb. Over 1,500 people were injured, primarily by flying glass. The terrifying question was, why did no one see it coming? The answer is the solar blind spot. Our powerful optical telescopes, designed to capture the faint light of distant stars, would be instantly destroyed if pointed anywhere near the Sun. If an object approaches from the direction of the Sun, it is completely invisible until it enters the atmosphere. The Chelyabinsk bolide exploited this flaw, using the Sun as a perfect gravitational cloak. This incident confirmed that our civilization has a massive, unaddressed vulnerability: the daytime sky. Furthermore, the Chicxulub asteroid was a C-type carbonaceous chondrite, a dark, coal-black object. Finding a black rock against the blackness of space with optical telescopes is nearly impossible. We are effectively blind to objects that do not reflect light well, confirming the need for a new generation of heat-sensing technology. The shield of Earth and the arsenal of planetary defense. The Chelyabinsk incident and the catastrophic scale of the Chicxulub disaster forced humanity to acknowledge its vulnerability and transition immediately from passive observation to active planetary defense. A new era of astronomical observation is upon us. In the Chilean Andes, the Vera C. Rubin Observatory is nearing completion. This facility is not a conventional telescope. It is designed to be the universe's first panoramic video camera. At its core is a 3.2 gigapixel camera, the largest digital camera ever constructed. Its mission is to scan the entire visible southern sky every 3 nights. By comparing the before and after images, sophisticated algorithms can instantly detect anything that has moved: asteroids, comets, and cosmic debris. The Vera Rubin Observatory is expected to increase our catalogue of known asteroids tenfold. However, ground-based optical telescopes cannot solve the solar blind spot or the dark asteroid problem. For that, we need heat vision from space. NASA is preparing the NEO-Surveyor Space Telescope. Its launch is planned for the late 2020s. NEO-Surveyor will be positioned at the L1 Lagrange point, a gravitationally stable point between the Earth and the Sun. From this vantage point, it can look away from the Sun, but also peer into the daytime trajectory, the exact blind spot that protected the Chelyabinsk meteor. Because an asteroid, however dark, is always warm from the Sun, NEO-Surveyor's infrared vision will see these objects shining like embers against the cold darkness of space. Its mandate is to fulfill the congressional task of finding 90% of all city-killer objects, 140 meters and larger, within 10 years. Finding the bullet is the first step. Deflecting it is the last. When planning an interception 10 to 20 years in advance, nuclear detonation, the Hollywood favorite, is the worst choice, risking fragmentation into thousands of radioactive projectiles, shrapnel effect. The most elegant and safest methods require time. 1. Gravity tractor. A heavy spacecraft is parked next to the asteroid. Its tiny gravitational pull is enough to gently tow the asteroid, centimeter by centimeter, off its collision course over years. 2. Laser ablation. A satellite fires powerful lasers onto a spot on the asteroid's surface, vaporizing the material. The resulting jet of gas acts as a tiny rocket exhaust, subtly nudging the asteroid. The most mature and tested option is the kinetic impactor, a simple game of cosmic billiards. This theory was tested by the DART, Double Asteroid Redirection Test, mission. On September 26, 2022, the DART spacecraft, a 570-kilogram projectile, slammed into Dimorphos, a 160-meter moonlet orbiting the larger asteroid Didymos at over 6 kilometers per second. The target was chosen because its orbital period around Didymos, 11 hours 55 minutes, could be easily measured from Earth. The result of the collision was a spectacular success that exceeded all expectations. Scientists had set the mission's success benchmark at a change of just 73 seconds in the orbit. Instead, the orbital period of Dimorphos was shortened by a staggering 32 minutes. The reason for this overwhelming effectiveness was the nature of the asteroid. Dimorphos was a rubble pile. The impact didn't just transfer DART's momentum, it ejected thousands of tons of material into space, which acted as a powerful reactive thruster, providing a massive additional push. This ejector-enhanced momentum, beta factor greater than 3, proved that humanity can intentionally alter the path of a celestial body. The Great Filter and the Dawn of the Cosmic Species. The story of the Chicxulub killer is ultimately the story of human intellectual awakening. We began as frightened creatures, creating myths to explain the lights in the sky. We became curious observers, chipping away at clay in the Gubbio Gorge. We became detectives, painstakingly reconstructing a 66-million-year-old crime scene from microscopic forensic evidence. And now we are becoming the planet's self-appointed defenders. The ultimate ethical question is upon us. With this great power comes great responsibility. If we must deflect an asteroid, who holds the authority to decide if the diverted trajectory targets the Pacific, the Atlantic, or a landmass? Planetary defense is not merely a question of astrophysics. It is a question of global politics and trust. The asteroid threat is the only true unifier, a danger that ignores all borders. In the decades to come, we will achieve the transparent sky era. We will catalogue nearly every major object in the solar system, replacing the ancient fear of sudden celestial death with confident, predictive knowledge. Our descendants may look at asteroids not as threats, but as resources, vast reservoirs of metals and water, turning former enemies into stepping stones for our expansion into the cosmos. There is an established concept in astronomy known as the Fermi paradox. If the universe is infinite, where is everybody? One proposed answer is the Great Filter, the idea that on the path to becoming a spacefaring civilization, there is an immense, challenging barrier that few species overcome. This barrier could be self-destruction, nuclear war, or ecological collapse. It may also be the simple existential threat of an asteroid impact. The dinosaurs, magnificent and dominant for 150 million years, failed the test. They had no cosmic program. We are the first generation of life on Earth to hold the steering wheel. We are transitioning from a planetary species, reliant on the capricious whims of nature, to a cosmic species, masters of our own destiny. The story of the Chicxulub killer did not end 66 million years ago. Its true legacy is here, in us. We exist because of that impact, and our mandate is to ensure that we are the last generation to be defined by a catastrophe we could not prevent. We are watching, we are learning, and we are ready to act. If you feel your eyelids growing heavy, allow the grand story of life on Earth to wrap around you gently and guide you into calm. Don't forget to subscribe to listen to more of our bedtime stories. Close your eyes, take a deep breath, and slowly drift into sleep, into silence, into the boundless, timeless current where all life intertwines. wishing you a quiet, comforting night.